Continuity and asymptotes. One of the most important properties of the majority of functions that model real-world behavior is that they are continuous. Graphically, a function is continuous at a point if the graph does not come apart at that point. If it doesn't have any breaks in that location, then you say that it is continuous. Graph A is a picture of a function that is continuous. Basically, as you move along the function, say we start here, as you move along the function, you don't have any breaks. Okay, you don't have any spots where the graph is separated. And most functions that we look at tend to be continuous, so you might not really notice anything interesting about that one. However, graph B shows us something that is referred to as a hole. As you move along the graph here, you have an open space located there. We say that there is a hole where x is equal to a. Okay, at some x value, there's a hole in the graph. There's a break, which means this has a discontinuity. It's broken apart. This particular type of discontinuity is a removable discontinuity because at that spot, at that hole, if you look above it, there is a value for f of a. Okay, as you evaluate the function for whatever values of x, you're getting all these outputs that would run along the graph, but at that one spot, it just jumps to a different location that's over here. There is a break in the graph, so we have discontinuity, but it has a point in another location above it that you could just move to that location. Now, you're not really allowed to move them. It's just a perception that if you could move it, you could patch that spot so that it becomes continuous. So we call this a removable discontinuity. Graph C also shows us a picture of a removable discontinuity. The graph basically looks like what we saw for graph B. We do have a hole here at A. We do not have a value that is located above it or maybe below it that you could push into that spot and patch it. However, if you could imagine creating a value that would easily plug into that spot and make it continuous, we can still refer to this as a removable discontinuity. Okay, so we have two different cases where you can have a hole. The point that would patch it could be in existence in the function, just at a different height. You could also have a case where that value just doesn't exist at all, which is more likely the ones that you'll run into. Okay, so graph C is a lot like B, it just doesn't have that other point. We still refer to it as a hole, and we still say that it has a removable discontinuity. Graph D is different. We have discontinuity here, again at that A value, but this would be referred to as a jump discontinuity. There's a bigger break here, and we can't patch this one. Not that you can really patch the other ones, it's just something we imagine that you might be able to do. But there would not be some quick fix to this. The only way to make this continuous would be to take this part of the graph and translate it down so that it matches up to that point. Okay, so a hole or a removable discontinuity is something that you can easily fix by just plugging in a point. And again, you're not allowed to do that, but it's just the visual of how we might perceive this. A jump discontinuity, you can't patch. You would completely need to move parts of the graph around to do that. Graph E is another example of discontinuity. We would call this infinite discontinuity. Instead of having some sort of a hole or just a little jump that you've got, we actually have an asymptote. We have a vertical asymptote here. On the left side of the graph, as it approaches the asymptote, it heads in a down direction forever. On the right, as it approaches that asymptote, it moves in an up direction forever. So the gap between these is infinite in size. So we refer to it as an infinite discontinuity. For graphs D and E, in addition to calling them a jump discontinuity and an infinite discontinuity, we can also refer to these as non-removable. A removable discontinuity can be patched easily. A non-removable discontinuity cannot be patched easily. All right. For example 1, what we're going to do is describe whether a graph is continuous or discontinuous at x equals 2. Once we make that decision, we'll elaborate on the type of discontinuity if it has one. We're also going to state the domain and the range in interval notation. Okay, so in the prompt, we're asked about when x is equal to 2. Okay, so I want to draw attention to each of the functions that we have and why it's about 2. Each of these functions does have a factor of x minus 2. You have it here, you have it here, you have it here. And when you plug a 2 into that factor, you're going to get a 0. It would be 2 minus 2, which gives you a 0. Now, in two of these cases, you get discontinuity, which is going to be f of x and h of x, because when you plug that 2 in, you create a 0 in the denominator. And you can't divide a value by 0. For example, if you put the 2 in for both of these, you're going to get 5 divided by 0. And you can't divide by 0. It becomes undefined. And it actually creates, in this case, an asymptote at 2. We get a vertical asymptote there. Okay, so we do have a discontinuity. This will be non-removable. It would be an infinite it would be an infinite discontinuity. It is non-removable. And for the domain here, we're going to have negative infinity up to 2. We're going to use parentheses because it doesn't actually include the 2. Then it's going to pick up after that, go from 2 to infinity. All right, the range, we haven't really talked much about this yet. It's going to show up in just a little bit. We do actually have a horizontal asymptote, which is going to be at 1. Okay, and so just a little bit, we're going to talk about how we would actually figure that out. But the range here is going to be negative infinity up to 1. It's going to pick up at 1 and go to infinity. Okay, so range is measured from bottom to top. Okay, let's skip over to h of x because that also has the undefined situation. Now, when you plug in the 2 here, you're going to get the 0 for the denominator. But when you plug in the 2 for the top, you also get a 0. You end up with a 0 over 0 case. Okay, 2 squared is 4, 4 minus 4 is 0, which is not what happened over here. We actually had a 5 over 0. Okay, in this case, you get a vertical asymptote. But in the case where that particular value creates a 0 in the numerator and the denominator, it actually creates a hole at that spot. So you still have discontinuity. This is removable. You've got a removable discontinuity. You can also refer to that as a hole. The domain is going to be the same domain that we have for f of x. Okay, negative infinity to 2, but not including, picks up after that, goes to infinity. The range for this is going to be a lot like the range for f of x, except that our break is going to be at 1, 2, 3, 4. It's going to be at a height of 4. Okay, so the range is negative infinity. That would be coming from the bottom, goes up to 4, does not include it, picks up after that. All right, now g of x has the same factor. It has an x minus 2. But when you plug a 2 in here, when a 2 is plugged in, and you create that 0, it's not part of a denominator, which doesn't cause any trouble. It just multiplies by what would be a 5 here, where the 2 plugged in, you have a 5. It just multiplies by the 5 and creates a 0, which means that you get a coordinate, which is here. It is not a hole, it's just an intercept. All right, so this function is continuous. The domain is going to be all real numbers, negative infinity to infinity. The range does have a lowest point, which is here, but then goes on to infinity. And that lowest point, the y value for the lowest point, you can actually figure out by plugging in the x value that would correspond to it, which is going to be halfway between these intercepts. Okay, so we got -3 and 2 as our intercepts, which would put the halfway point right here at -0.5. So I'll plug that in. Let's do that up here. Okay, so we got -0.5 plus 3 multiplied by -0.5 minus 2. Okay, that is going to give us 2.5 times -2.5, which that is going to be equal to -6.25. Okay, so this function starts on the bottom end here, starts at -6.25. 6.25, and that is actually included. So we're going to use a bracket for that one, and goes up to infinity. As mentioned before, I was going to talk about how we would identify a horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if f of x approaches a limit of b as x approaches negative infinity or positive infinity. Okay, there's a lot going on in there. Let's go ahead and take a look at the notation and I'll explain what it all means. Okay, the first part right here is going to talk about negative infinity. This is going to talk about positive infinity. What we're going to be looking at is taking the limit as x approaches negative infinity. In other words, what it means is we're going to look at what happens to the function as you plug in bigger and bigger negative numbers into the function as you're moving way out to the left. Okay, like negative 100, negative 1,000, negative 1,000,000. What happens to the graph as you move really far out to the left? Does it approach a certain value, b, like a certain height, a certain output? This is kind of the opposite. What happens as we plug in larger and larger positive numbers? What happens as we plug in a positive 100, a positive 1,000, a positive 1,000,000? Does that function start to level off at some number? In example 2, the function that we're going to look at, the horizontal asymptote is going to be a little bit difficult to see in the graph that I gave you, but this is what it is. The horizontal asymptote is going to be the x-axis. Okay, a piece of the graph, okay, so that would actually be y equals 0. A piece of the graph is here, and it does pass through the x-axis right at the origin and goes through. Okay, now you've got another piece of the graph here, okay, and if you were to follow out to the left, the negative infinity direction, you're going to see it's beginning to approach that x-axis. And what it does as it continues out is it gets infinitely close to that line, but never actually makes contact with it. The graph begins to level off at 0 from the bottom side. On the right, you can only see a little bit of the graph here, but it does the same thing that we see here from the top side. It begins to get closer and closer to the x-axis, and as you go further out, it levels off at that spot. And that's what the horizontal asymptote is going to look like in the graph. All right, so then the question is, how do we actually take the function and get the horizontal asymptote from there? Okay, the idea behind it is to imagine plugging in really, really large numbers, like plug 100 in or 1,000 in for x and see what happens. Now, if I were to plug in 1,000, if I were to plug that in, I would be thinking about what's happening as I go out to the right. If I plug in a negative 1,000, I'll be thinking about what happens as I go way out to the left. Now, before you start plugging in values and doing a lot of work, an important note we can make here is that you can look at the numerator separate from the denominator. Okay, in the numerator, all you have is an x, and that's just going to stay as it is. In the denominator, you've got 3 terms. You've got the x squared, you've got the x, you got the 2. If we were to plug in 1,000 here, to plug in the number 1,000, 1,000 squared is going to be 1,000,000, a huge number, and this is still just 1,000. So you'd be subtracting 1,000, which is a big number, but it isn't nearly as big as 1,000,000. You're going to be subtracting 1,002 from it. And if you plugged in an even larger number, this would grow incredibly fast compared to whatever you had here. Even if you plugged in 1,000,000, you're going to be looking at 1,000,000 squared here. Okay, so what we're allowed to do is eliminate the weaker terms and just focus our attention on what we call the leading terms for the numerator and the denominator. Okay, so we can think of this as just x over x squared. And now that the top and the bottom both have a single term, we can think about reducing them. And this reduces to 1 over x. Okay, and that's what we're going to think about putting really large numbers in. If we put a really large positive number in there, like 1,000, you get 1 over 1,000, which is pretty darn close to 0. If you divide 1 by 1,000, it's close to 0. If you plug in 1,000,000, you get even closer to 0. Okay, so we see that this is actually going to get closer and closer to 0 as you plug in larger numbers. On the other side, when you plug in a negative number, it still approaches 0 because you're dividing by a larger and larger number, but it's always going to be a negative answer, and that explains why this is underneath the asymptote. But in the end, the bigger and bigger numbers you plug in there, we are approaching a certain value, which will be 0 in this case. All right, vertical asymptotes. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if f of x approaches a limit of negative infinity or positive infinity as x approaches a from either direction. Okay, in a way, how we describe this limit is kind of backwards from the horizontal asymptote. Okay, we're going to look at x as it approaches a particular x value, not infinity or negative infinity. This indicates that we're approaching the x value, and we're calling it a here, from the left, from the negative side. So we're coming in from the left. Okay, now if that limit goes to infinity or negative infinity, which means that at that spot, the graph either takes off up forever or takes off down forever, you get positive or negative infinity. And that'll create that vertical asymptote. Okay, in the other one, we're approaching that value from the right side, from the positive side. If the graph takes off up forever, that would be positive infinity, or down forever would give you negative infinity, and that would create a vertical asymptote as well, which we can see in the picture here. We've got the graph taken off forever that direction, forever this direction, same thing here and here. Okay, so we have vertical asymptotes at -1 and +2. So again, how do we get that from the equation? The trick is to figure out what x's will make this undefined. In other words, what makes the bottom equal to 0? Okay, so this is a standard form quadratic. What I'm going to do is factor it. What two values multiply to give me -2 and add to give me -1? That would be a -2 and a +1. And the value that I could plug into this spot to create a 0, making the whole thing 0, would be 2, this 2. The value that I can plug into this x that would make the whole thing 0 would be a -1. And that's where you find your vertical asymptotes. Okay, with one catch here. If you go back to example 1, we had a function called h of x. And that's what h of x will look like. If I factor the top, this is the difference of squares, I get x plus 2 times x minus 2. And I have the denominator, x minus 2. Okay, now if I were to base things strictly off of what I said here, I'd get a vertical asymptote at 2, because that makes it undefined. However, if that value of x that makes the denominator 0 also makes the top equal to 0, okay, those match up to each other. If that happens, you don't actually get an asymptote, but you get a hole. You get a removable discontinuity. So there's a little catch there. If these values that you think are going to be vertical asymptotes make the top 0, neither of these do, it becomes a hole. Otherwise, those are your vertical asymptotes. All right, so the horizontal asymptotes can give us one kind of end behavior. It can tell us what the graph does as it goes further out to the right or further out to the left. For example 4, we're going to state the end behavior as a limit of f of x as x approaches infinity or negative infinity. So we have to address how it looks on both sides. Okay, this is going to be coming back to the idea of the horizontal asymptote. So most likely we're going to get the same answer when we move out to the left or move out to the right. Okay, now however, if a graph does not have a horizontal asymptote, because, well, most graphs that you've looked at don't actually have a horizontal asymptote, the end behavior may be positive or negative infinity. And to answer these questions, what we're going to do is take the function that's provided, we're going to eliminate the terms that are not leading, reduce, and see what would happen as you plug in really large numbers. Okay, so for a, the leading term in the top is the only term that we have, which is the 3x. In the bottom, it's going to be the x squared. So we're going to take out the +1. That'll leave us with 3x over x squared, which can reduce by a factor of x. So we get 3 over x. Okay, so the top is a constant, it's a 3. But don't really pay too much attention to that, because it could be any constant. It could be a constant of 1,000. Okay, what's important here is that the denominator is an x. And as we plug in really large numbers for that denominator, and the numerator stays constant, when the bottom gets larger and the top stays the same, we're going to get closer and closer to 0. You're going to continue to divide by a larger and larger number. you're going to get less back. So it gets closer to 0. And that's going to be true whether you use very large negative numbers or very large positive numbers. Okay, in both cases, it's going to settle off at 0. And you do have a horizontal asymptote at 0, which is the x-axis. Okay, for b, we can take out the plus 1. For the top, we've got the 3x squared. For the bottom, you've got x squared. And in this case, the degree of the top and the bottom are the same. So when it reduces, all the x's cancel, and you get 3. We actually create a horizontal asymptote at 3. So whether we go out to the left or the right, I mean, there's no x in here at all anyway, whether you go out to the left or the right, it's going to settle off at 3. And for function c, we again can take out the plus 1. The top is going to be 3x cubed. The bottom is going to be x squared. And as this reduces, you divide out all the x's in the bottom. So that'll just become a 1. You get 3x. Okay, all the x's in the denominator cancel. You lose 2 of them in the top. So you still keep 1, you get 3x. So in this case, as you plug in very large numbers for x, it continues to grow. Okay, if you plug in 100, you get 300. If you plug in 1,000, you get 3,000. The bigger the x, the bigger you get. This does not actually settle at a number. It actually goes off to infinity. When you plug in very, very large positive numbers, it goes to positive infinity. The graph is going to take off in an upward direction. However, if you plug in very, very large negative numbers, the graph isn't going to take off this way. We're moving that direction because we're using larger and larger negative numbers. We're going in the left direction, and you're getting larger and larger negative answers from it. So the graph is heading in this direction. It's heading that way. It's actually going down, which would be negative infinity.
Later, blah.